Okay, so electromagnetic induction. So electromotive force and motional electromotive force. So we'll look into it briefly. So very briefly, we have this electromagnetic induction, or just write it simply. And right away get to the Faraday's law without wasting time. And it says that the electromotive force is proportional to the number of turns in the solenoid or the coils, and it's also proportional to the rate of change of magnetic flux, which is technically equal to electric flux, rate of change of magnetic flux, time rate of change of magnetic flux. And if we combine the two, this and this, we get a proportion. Electromotive force is directly proportional to n delta phi b by delta t. Yes, and k is equal to 1 in system international units, and wait, k, now we convert the proportion into equation. So E is equal to kn delta phi b by delta t. Yes, now we put k is equal to 1 because k is equal to 1 in system international units, so E becomes n phi b by delta t. Okay, delta t. Okay, where n is the number of turns and E gives you the electromotive force. So we can also go further with the field area and angle type of relationship that we have in the basic forms. And it's interesting because motional electromotive force is related to motion, which implies the use of velocity. Yes, so EMF, electromotive force, motional, instead of starting over, we rather Continuing. So for unit form, here n is the number of turns, and n can be 1 for a unit form. Okay, so phi b by delta t is equal to electromotive force in unit form. Yes, and phi b, we know that it is equal to ba cos theta. Yes, this is established in the fundamentals of magnetism. Yes, and cos theta is approximated to 1 because theta is approximated to 0 degrees. Okay, so we use a simple version. Phi b is equal to ba. Yes, so this is a usable form. Let's not number it right now, but this is a usable form. And how so? We'll see. So continuing on the other half of the board, we write phi b is equal to b delta a. Okay, now I didn't write a, and I'm writing delta a because this is a differential area. Okay, and this is where, as you're working with the unit form, so we're talking about a differential area b delta a, and differential area is basically delta a is equal to a2 minus a1, which is equal to L2x minus L2 L1x. Yes, because length, the third dimension remains the same, but the length changes in the coil of the solenoid. Sorry, the length remains the same. Yes, and the third dimension changes, lx2 minus lx1, so it gives us lx2 minus x1 for delta a. Okay, or it gives us L delta x for delta a, which we can use. Once we have this, we have the form for phi b is equal to b L delta x. Yes, and now we can put it in the form for E, which says what? Which says b a. Okay, phi b is equal to b a. Yes, phi b is equal to b a, and E is equal to phi b by delta t. So phi b is equal to b delta a, and E is equal to phi b by delta t. This is for unit version. So what happens is, you see, we're getting close. E is equal to b delta a by delta t. E is equal to b L delta x by delta t, and E is equal to BLV. Okay, so this is a form of interest here, BLV, field, length, velocity in magnetism. And if you're interested in the vector version, then we introduce the sine theta, because it's electric field, magnetic field, and the force are all at 90 degrees perpendicular. So BLV sine theta. Yes, so this is the form we have in the end. Okay, so it's better to use this as the final form. because sine theta, if theta is equal to, if theta approaches 90 degrees, sine theta is about 1 and E becomes once again BLV. Okay, so we don't need to worry about the alteration of the form with sine theta. Yes, now we gradually go further. Okay, so what we have now is the mechanical power. And power is force times velocity, and it's I'll show you mechanical power in terms of magnetism. Mechanical power. So in mechanics, power is force dot velocity, and it's Fv cos theta. Yes, force, velocity, and cos of the angle. And the magnetic force is equal to, as we know, ILB sine theta. Yes, which can be approximated to ILB, which can be approximated to uh, okay, which can be approximated to ILB, because sine theta can be 1 if the angle is 90 degrees, if we take the approximation. And then the next thing is power, which says it is force times velocity, IBLV. Okay, once again it can be with the cos theta, but then if the force and velocity have parallel inclinations, the directions are parallel, so this can very well be ILBV P. Okay, so we need, we keep this in mind, and then we keep this in mind. Okay, and then we go further, and what we have is this basically, but then there are approximations. Okay, so yes, and we also know that uh, as V is equal to IR, simply electromotive force motion can also be approximated to IR. Yes, because when there is a source of voltage involved, there's motion electromotive force also involved, so these approximations do work. Okay, so let's call them A and B if needed for substitutions. Okay, so I is equal to E by R, and what do we have for E? For E we have, as already established, E is equal to I L B V, yes, I is equal to L B V. Okay, so now I is equal to L B V by R, and if you have this situation, So we can use this I in the form for power. We have a form for power in 4 which says P is equal to ILBV. So let's say P is equal to ILBV, and so P is equal to ILBV, and I is equal to P by LBV. Now we can equate these two. LBV by R is equal to P by LBV. What happens is cross multiply. PR is equal to LBV whole square. P is equal to L square B square V square by R. So this becomes a form for power, and this is worth noticing. And for dissipation, for example, for power dissipation, um, let's do it on this side of the board. We have lots of space, so dissipation, P is equal to VI, we know, and V is equal to IR. So P is equal to IRI. Yes, P is equal to I square R. This is the form. Let's call it 8 in the situation here. And I in 5 is VLB by R. Yes. VLB whole whole square, basically. Just a little reminder here. So for dissipation we need to have resistance incorporated. So I is equal to this here. So you see from 5, I is equal to VLB by R. So I square is equal to V square L square B square by R square. Yes. So power with the resistance, which implies the dissipation, is equal to V square L square B square by R square dot R. R reduces in the denominator, because there's one in the numerator as well. V square L square B square by R, or power dissipated is equal to VLB whole square by R, if I am not wrong, and it seems to be very correct and legitimate. Okay, so we have this. It's very much developed. So we move further. And discuss the self-induction. Self-induction. Yes, so we discuss the self-induction. Self-induction. And it says that the electromotive force, basically we know it starts